Swayam Prabha. Digital India. Educated India.
Hi everyone, welcome again to the course of structural biology. We are continuing with various structural biology techniques. We have discussed about X-ray crystallography. Now we are in the module where we are discussing about nuclear magnetic resonance. In the last class I have started introducing NMR. I talked about basic application of NMR, the very basic concept, introductory concept of spectroscopy, and few ideas regarding NMR. Today we will talk about magnetism, we will talk about nuclear spin, we will talk about different energy level, and also we will talk about instrumentation in NMR. In addition to that, I would also let you know about some major contributors in the field of NMR spectroscopy. So, let us start with, so in NMR, nuclei with an odd mass or odd atomic number have nuclear spin in a similar fashion you see in a spin of electrons. This includes 1H proton and 13C, but not 12C. The spins of the nuclei are sufficiently different that NMR experiments can be sensitive for only one particular isotope of one particular element. We talked about little bit in abundancy and all. The NMR behavior of 1H, the proton, and 13C nuclei has been exploited by organic chemists and structural biologists, since they provide valuable information that can be used to deduce the structure of organic and bio compounds. Our demonstration would be majorly based on these two elements, because if you look at in protein, they are the major network, in any polymer they are the major network, in any small molecule they are the major components, but we would also talk about others when needed. So, as I told, NMR spectroscopy, it have three component as the name suggests: nuclear, magnetic, resonance. Yesterday in the last class we talked about nucleus, today we will talk about resonance, and in between there is magnet and magnetic property. So, let us come to the concept of magnetism. Since a nucleus is a charged particle in motion, it will develop a magnetic field. 1H and 13C have nuclear spins of half, and so they behave in a similar fashion to a simple tiny bar magnet. So, if you see, when there will be no field, they are disorganized in their orientation like this, and when a field is applied, they would be properly oriented. These nuclei together in a sample are oriented randomly in absence of magnetic field, as I talked about. A combination of spin and a charge confers the nuclei with properties of a magnet. So, a magnetic dipole moment is associated with every nucleus. As a result, every nucleus which has a charge and spin becomes now a magnet, a tiny small magnet. In the absence of the magnetic field, these are randomly oriented, but when a field is applied, they line up parallel to the applied field, either spin aligned or spin opposed. So, see, there are two conditions: spin aligned and spin opposed. We will talk about them. Nuclear spins are oriented randomly in the absence of a magnetic field, but have a specific orientation in the presence of an external magnetic field B0. Some nuclear spins are aligned parallel to the external field, as I told. They have lower energy orientation and more likely. So, if you see here, they were randomly oriented, and when applied field is there, they are aligned, and some are aligned on the direction where the applied magnetic field is given, whereas others are opposite to that. So, some nuclear spins are aligned anti-parallel to the external field. If you see, the pinks are aligned with the parallel to the external field, whereas the blue ones are anti-parallel to the external field, and in this case there would be higher energy orientation and less likely. By more likely and less likely, I mean more populated and less populated. In the lower energy, in the stable state, there are more populated, more nuclei would be there. In the higher energy, which is coming through like opposite anti-parallel alignment, it is less populated. So, from there we are getting the concept of two spin states. In NMR, electromagnetic radiation is used to flip the alignment of nuclear spins from the low energy spin aligned state to the higher energy spin opposed state. So, you see that there are two energies, and there is ground state and excited state, and there happen spin flip. The energy required for this transition depends on the strength of the applied magnetic field. So, here the applied magnetic field, the external magnetic field have a very critical role, because the flipping depends on the amount of energy provided. The energy difference between the spin states is quite small and correspond to the radio frequency range of the electromagnetic spectrum. We have talked about that NMR is used radio frequency, and this is one of the reasons. So, why radio frequency? Because it is good enough to spin flip, which we want here, and because it is low energy, this enables NMR to be non-destructive, non-invasive. And when we talk about non-destructive, non-invasive, there are many applications, but what comes first in our mind is MRI, which is a really good technique by which we could now identify a lot of disease conditions. So, as this diagram shows here, the energy required to cause the spin flip del E depends on the magnetic field strength at the nucleus. With no applied field, there is no energy difference between the spin states. So, there are two spin states, we understand them, but without any external applied magnetic field, there is no difference, the del E is 0. But then you start increasing the application of external magnetic field, there is distance. So, when you apply, let us say x amount, it is del E. When you apply 2x amount, it is del E prime, and it is easy to understand that del E prime is greater than del E, because the applied magnetic field BO is greater than BO prime is greater than BO. As the field increases, the separation of energies of the spin state increases with the frequency required to cause the spin flip. Magnetic dipole moment and gyromagnetic ratio. As I talked about, the tiny magnets are randomly oriented in absence of external magnetic field and oriented when magnetic field is applied. Now, if we consider I being the net nuclear spin number, then the nucleus could only stay in spin states 2I plus 1, which means in spin state 2 for 1H proton or 13C, according to the rules of quantum mechanics, there would be, so it is 2I plus 1. So, if it is half spin, 2 into half plus 1, which is 2. So, there are 2 spin states. If you look at the nucleus now, which has a magnetic dipole because of its charge and spin. So, from where it is happening, we know the nucleus have charge because of the charged proton, and it have spin because all the nucleons, both protons and neutrons, all have spin. So, because of its charge and spin, the magnetic dipole moment mu is equal to gamma into I. The parameter gamma is basically a constant for a particular type of nucleus. It is known as gyromagnetic ratio. So, what you have to remember here, particular type of nucleus. So, gamma varies depending on particular type of nucleus. The gyromagnetic ratio is an important parameter which is useful for understanding NMR. The gyromagnetic ratio of a particle or system is the ratio of its magnetic moment to its angular momentum, which is here called as nuclear spin angular momentum and denoted as I. So, gamma is the ratio of its magnetic moment with angular momentum. The SI unit is the radian per second per Tesla, or equivalently the coulomb per kilogram. Mu is a vector quantity because it has a direction, and similarly I is a vector quantity because it has a direction. So, both mu and I both have direction. So, because mu have direction, some it is a vector, it have a direction. So, what you could do? You could split it into different directions. Let us consider you split it into x, y and z. So, there would be 3 components, mu x, mu y and mu z. When we apply a magnetic field, this magnetic dipole interacts with the external magnetic field, and the energy of this interaction is given by the formula energy equal to minus mu into B0. B0 is the external magnetic field. This is a dot product because of its vector property with the magnetic field. So, it is a multiplication, but a dot product because of the vector property. So, as I said, we can split mu as mu x, mu y and mu z, and the magnetic field B0 can also be split as Bx, By, Bz, which are the components of the magnetic field along the 3 different directions. This dot product can therefore be written as E equal to mu x Bx plus mu y Bi and mu z Bz. Assuming that we apply the magnetic field in the z direction, what happen is there would be no x and y component, like because they are 0. So, because they are 0, the total component is 0. So, it would be this, and therefore, only z component is mu z Bz, this will remain. So, now E equal to mu z and dot Bz. Now, this mu z is nothing but gamma into Iz, where Iz is the z component of the spin angular momentum, because spin angular momentum is I is also a vector, could be dissected into 3 coordinates. So, we only get the z coordinate. So, this is our external magnetic field B0, which we have applied in the z direction, and therefore, the total final energy of the interaction becomes equal to E equal to minus B0 gamma Iz, that is the total energy. We are talking about spin states, we see that there is possibility of two states developed. According to quantum mechanics, if you have a spin I, it has a possibility of 2i plus 1 spin states. We talked about this. So, what is a spin state? Spin state is basically what we could refer to discrete energy levels. Similarly, the energy levels corresponding to this angular momentum, which is denoted by I, is also quantized, and it has 2i plus 1 different levels, which I talked about just before. So, for example, when I equal to half, which is the case of protons and carbon 13, 2i plus 1 equal to 2. So, that means the hydrogen atom or hydrogen nucleus has now two spin states, that is denoted as plus half and minus half. That means this Iz has two possible values, Iz equal to half h by 2 pi or minus half h by 2 pi, where h is Planck's constant. Now, if we put this value of Iz in the equation for the energy of interaction E, it results in E equal to B0 gamma half h by 2 pi or minus B0 gamma half h by 2 pi, depending on the value of Iz we use. So, two different state, again energy state. We can see that now this energy of interaction has two values depending on whether the spin is either in the plus half or minus half state. So, therefore, what has happened that we have created two energy levels because of the interaction of this nucleus with a external magnetic field. One energy level correspond to the lower energy value, which is when the spin is in the plus half state, that is the ground state energy level, also called as the alpha state. So, we talk about energy splitting. The lower state is alpha state, and we will see the higher state is beta state. When Iz equal to minus half, the total energy is positive as shown here, and that becomes the excited state energy level and is called as the beta state. The difference between two energy levels become del E equal to B0 gamma half h by 2 pi minus B0 gamma half h by 2 pi equal to B0 gamma h by 2 pi. The nuclei now get distributed between two states, as I told, alpha state and beta state. When we apply a magnetic field, which is we are calling as B0, and put a sample in that magnetic field, all the nuclei in the sample are exposed to the field and get distributed into one of the two energy levels. So, you have sample, there the nuclei are randomly oriented, you apply external magnetic field, you have two states, lower energy state which is alpha state and higher energy state which is beta state. With this, in the terminology of nuclear magnetic resonance, we have looked at the nucleus and the magnet and the interaction between the nucleus and the magnet. Now, the next term is resonance. So, we talked about nuclei, we talked about magnet, and now it is resonance. What happens next is essentially that we supply an external energy which will take the molecules from the ground state to the excited state. So, we need this. So, we have to provide an external energy. This energy has to match the gap between the two energy levels denoted as del E, and if it match, only then the molecule will absorb the applied energy. The matching of the gap is a critical concept and is also a generalized idea of spectroscopy. So, if you look at spectroscopy, for different type of spectroscopy, we target different things, we have different rays, but there is a gap and there is a resonance to find the gap or matching the gap. When we apply an energy which matches this energy level gap, it is called resonance. In resonance, the molecules which are now in alpha, the ground state level, get excited and they absorb the energy and go to the beta state. And in this moment, we justifies the term nuclear magnetic resonance, because we talk about different nuclei, we talk about how these tiny magnets are formed because of charge coming from proton, spin coming from nucleon, and now we know the resonance, the matching of the gap. So, these different nuclei, tiny magnet with charge and spin matching the gap, develop the technique called nuclear magnetic resonance. So, let us come to the overall idea of NMR. You have to take a sample which contains molecule in which atoms have non-zero nuclear spin. If you have zero nuclear spin, you will not get any effect. So, you have to be knowledgeable about the fact that the sample you are picking up should have atoms or at least an isotope of an atom which have non-zero nuclear spin. Keep the sample in a magnetic field, consider the magnetic field is applied along z direction. So, you could put it in any direction, but let us put it in z direction, so that other two would be not present, like nullified, making your case simpler. The molecules now get distributed into two populations with one set of nuclei in the alpha state and other set in the beta because of their interactions with the magnetic field. Take the molecules which are in ground state to the excited state by applying an energy which is equal to the difference in energy level, that is delta E. So, what happened? You have this one state and another state in same energy, where del E equal to 0. Now, you apply energy. So, they are going to different places calling alpha and beta, and now you have to put energy to match. That is what more or less basic principles of NMR is. This process is called stimulated excitation and stimulated emission. So, therefore, the total net energy absorbed will depend on the difference in the population of how many nuclei are in the ground state minus the nuclei in the excited state. In case if they are equal, then there would be no net excitation and the signal would be 0, there would be no signal. That means no energy would be absorbed. But if the difference in the population between the ground state and the excited state is not 0, and if the ground state is more populated than the excited state, there will be more number of nuclei absorbing than the nuclei coming down from the excited state to the ground state, which is the matching energy, and that is where the signal comes. In summary, there will be a net positive absorption of the energy, and that is what we rely on in NMR. That means all depends on the net difference. The word difference is very important here in the population of the two states, the alpha and the beta state. The concept of population difference, as I talked earlier, is applicable in general across all spectroscopy. Wherever we talked about energy quantization, we talk about population difference and distribution, and hence their matching. That distribution comes from a famous law which is known as Boltzmann law. Boltzmann law says that under equilibrium condition there is always more population in the ground state compared to the excited state. That means under standard condition you will always have more nuclei which are sitting in the ground state than the number of nuclei which is present in the excited state, and the ratio of the population between the two states is given by the write up which we are putting on the Boltzmann equation. Coming to the strength of the magnetic field. The strength of the magnetic field is given in different units, Tesla, Gauss or megahertz. 1 Tesla equal to 10 to the power 4 Gauss. The most common way to indicate the magnetic field strength is to give in terms of Larmor precision frequency. The frequency of precision, the frequency at which the magnetic nucleus precedes around magnetic field is given by this frequency nu equal to gamma B0 by 2 pi. Now, here B0 is measured in units of Tesla or it can be in units of Gauss. If we put in the values of gamma and B0 which is typically used, we get nu in the megahertz regime. So, if you see when we get 7.05 Tesla, this is actually in megahertz 300 megahertz. 11.75 Tesla is 500 megahertz, 16.45 Tesla is 700 megahertz and 21.15 Tesla is 900 megahertz. And that is why you see that we use megahertz to say the power of the NMR instrument. The table I showed you clearly tells you the fact that why NMR system mentioned in terms of megahertz. We say that we have a 300 or 400 megahertz spectrometer. So, essentially the magnetic field is what is determining the frequency. When somebody says that he or she has 500 megahertz NMR spectrometer in the laboratory, what he or she means to say is that a magnet which is 11.75 Tesla. So, the point here is that the resonance frequency depends on the magnetic field directly. To put this in perspective, the earth's magnetic field is very small which is 0.5 Gauss. So, the magnetic field we use in NMR is really orders of magnitude higher compared to what earth magnetic field is. We use very strong magnetic fields and the associated precautions which has to be taken will be considered when we discuss about the hardware aspect. When nuclei that are aligned parallel with an external magnetic field are irradiated with proper frequency of electromagnetic radiation, the energy is absorbed and the nuclei spin flops to the higher energy anti-parallel alignment. Nuclei that undergo spin flips in response to applied radiation are said to be in resonance with the applied radiation nuclear magnetic resonance. Frequency necessary for resonance depends on strength of the external field and the identity of the nuclei. So, I talked about the NMR spectroscopy, the nucleus, we discussed the resonance, we discussed, and the magnetic property, magnetism we discussed. Now, we will talk about the hardware of this. So, we will discuss NMR hardware. But before going to NMR hardware, I would also like to give you a brief history of how NMR as a technique developed. In 1938, NMR in molecular beams by Rabi from Columbia University, who first have taken the NMR setup and NMR signal. In 1946, NMR of liquid and solids are performed by Purcell, Torrey and Pound from Harvard University, Bloch, Hansen and Packard from Caltech University. In 1952, the first commercial NMR spectrometer is developed. In 1962, the first superconducting magnet for NMR is created or designed. In 1968, first pulse Fourier transform NMR, which again revolutionized the process how NMR works. In 1969, the first concept of MRI scanner, which is now playing a very important role in medical science. In 1971, first 2D NMR experiment caused by Jean Jenner. In 1985, the first protein structure was solved. In 1985, as I told, Michael Williamson, Habel and Utrecht reported the first solution state protein structure, which is a proteinase inhibitor 2A from bull seminal plasma. Initially, they were met with a lot of disbelief. People were not agreed to what their finding was, and it was not until several structures solved initially using NMR were actually solved again using crystallography, and when they have found that the structure solved by NMR is having the similar information when solved by X-ray crystallography, then NMR was actually accepted, and in 2002 Utrecht was rewarded with Nobel Prize in Chemistry because of his contribution in solving protein structure. In 2009, the first gigahertz NMR spectrometer is developed. So, coming to the journey of NMR spectrometer instrument, in 1949 the first machine was developed, the very first NMR hardware setup. This was happened in Nobel laureate Felix Bloch's lab in Stanford, providing the first ever characteristic signals. If you see, they have taken ethanol and they get 3 signals, 3 peaks. We will talk about that later. In 1964, Traub-Tauber-Kiss won the first commercial NMR spectrometer, which was equipped by electromagnet, was arrived, and you see that how much change in the sophistication of the data collection. Then in 1970 HFX90 came. This is a bit better version of the first commercial NMR spectrometer equipped by electromagnet. So, then in 1985 AM console with cryomagnet, the first cryomagnet developed. So, this is a NMR spectrometer with the cryomagnet. In the year 2000, there was like fully commercialized and fully automated NMR instrument. So, you could only do a current routine, everything is automated, and in 2002 you see the present NMR spectrometer which is currently used. The research laboratories are equipped by several huge spectrometers with very high intensity of magnetic fields. So, the components of NMR spectrometer. The first one, which is very important, is magnet, superconducting magnet, SIM coils, liquid helium and nitrogen container, anti-vibration legs. Vibration is extremely critical. So, when the NMR instrument set, they have anti-vibration legs which absorb the vibration and not let the instrument getting the vibration. Probe RF coil to pulse and receive signals, gradients, temperature probes, lock coil, preamplifiers. Console, the electronics for generating RF, the radio frequency pulses, power and gradient amplifiers, lock system, temperature controls, etc. in the console. Computer for data storage, processing and analysis, communication with console. So, these are the major components. Now, if you see, this is a pictorial demonstration of major components. This is the superconducting magnet, generates a powerful magnetic field that is tens of thousands of times stronger than the earth's magnetic field. As I told, samples are placed within this magnetic field and exposed to radio waves. Spectrometer transmit and receives the radio frequency waves used to make the NMR measurement. The computer, the instrument control and data processing. So, what is the basic arrangement of an NMR spectrometer? The sample is positioned in the magnetic field and excited via pulsations in the radio frequency input circuit. The realigned magnetic field induces a radio signal in the output circuit, which is used to generate the output signal. Fourier analysis of the complex output produces the actual spectrum, which we are going to talk about. The pulse is repeated as many times as necessary to allow the signals to be identified from the background noise. You use more pulses and your signal would be enhanced and your signal by noise ratio would be improved. That is good for getting better data. So, this is again the basic setup. This is the external magnetic field. This is a dewar to hold the superconducting coils generating the external magnetic field. Here the sample is put and here the coil to supply and receive the radio frequency energy. The radio frequency energy comes from the NMR console and the data acquired, it generate the radio frequency energy and it get the data and send it to the computer. So, we are talking about superconducting magnets. What is superconducting magnets? The superconducting magnets are electromagnets made from coils of superconducting wire. They must be cooled to cryogenic temperatures during the operation. In its superconducting states, the wire has no electrical resistance and therefore can conduct much larger electric currents than ordinary wire, creating intense magnetic fields. Superconducting magnets can produce greater magnetic fields than all but the strongest non-superconducting electromagnets and can be cheaper to operate because no energy is dissipated as heat in the windings. So, if you see, this is the superconducting magnet. If you go inside, you will see that there are superconducting wires and this is the super fine high resolution demonstration. The superconducting coils are made of niobium titanium or niobium titanium alloy for high field strength. These wires are 1 miles long with uniform diameter throughout. The magnet is rested on vibration free legs, as I talked about, to avoid vibration from the ground to be transferred to the magnet. The higher the field strength, higher is the sensitivity of the NMR. The higher the field strength, higher is the resolution. So, when you increase the field strength, you increase the resolution. About this we will discuss specially when we are going to discuss protein NMR. The magnetic field is not constant and slowly drifts with time. Typical drift rate is 8 to 10 hertz per hour. So, this you have to include in your experimental consideration. Console. So, the purpose of the console is to house the various spectrometer units in a compact arrangement, as well as providing shielding from interference such as electromagnetic radiation from external sources. This is a console with a computer. Radio frequency signal generator, if you see here you will see two parts, decoupler and transmitter, both of them have amplifier as well as frequency generator. So, frequency generators and signal amplifiers are required for each radio frequency channels. Here we have shown one where it have two channels, this is one channel and this is the other one, but the modern spectrometers can have up to 8 channels. Probe. The probe is the part of an NMR spectrometer that does much of the work in terms of exciting the nucleus spins and detecting the NMR signals. The probe goes into the center of the magnetic field and the sample is inserted into the probe to perform the NMR experiment. The probe contains the radio frequency coils tuned at specific frequencies for specific nuclei in a given magnetic field. The probe also contains the necessary hardware to control the sample temperature when combined with an external temperature controller. So, these are probes which are used for solid state and these are probe which used for liquid. The RF coil which is necessary tuning the RF coil to the right frequency. The RF or radio frequency coils used in NMR spectrometers need to be tuned for the specific sample being studied. An RF coil has a bandwidth or specific range of frequencies at which it resonates, where the resonance happen. When you place a sample in a radio frequency coil, the conductivity and dielectric constant of the sample affect the resonance frequency. If this frequency is different from resonance frequency of the nucleus you are studying, the coil will not efficiently set up the B1 field nor efficiently detect the signal from the sample. So, the matching is very important. You will be rotating the net magnetization by an angle less than 90 degrees when you think you are rotating by 90 degrees. This will produce less transverse magnetization and definitely less signal. Furthermore, because the coil will not be efficiently detecting the signal, your signal to noise ratio will be poor. So, that is why it is very important to tuning the radio frequency coil to the right frequency. This is a collection I have made to show you that there are different NMR system depending on the magnetic power which we have already talked about. All of them are Bruker system where you see 300, 400, 500, 600, 800, 900, 1.2 gigahertz, which is the most powerful one up to now is present. There are in between, but these is how a system look like. So, I have talked about the basic concept of magnetism, the basic concept of resonance and the hardwares required for doing the NMR experiments. I will end up this class by talking about some people with their landmark contribution to the field of NMR. I talked about history before. Here I take people who are contributing in NMR and because of their contribution they are awarded with different prizes. One, the Nobel Prize winners, you all know about Nobel Prize, so I am not going to define that. I will also take the names of very young investigator awardees, who actually got this award for their achievement in any area of magnetic resonance, their contribution. The award is to be granted to people in the first 12 years after their PhD. So, they are mostly young investigators. And the Laukian prize on the name of Gunther Laukian, which is to recognize recent cutting edge experimental NMR research with a high probability of enabling beneficial new application. This prize was established in 1999 in memoriam of Gunther Laukian, who was a pioneer in NMR research. I will talk about Nobel Prize winners first. So, Otto Stern from US in the year 1943 for the contribution to the development of molecular ray method and his discovery of the magnetic moment of the proton. Isidore Rabi, I already talked about Rabi because he got the first signal. So, he is from US. He got Nobel Prize in the year 1944 for resonance method for recording the magnetic properties of atomic nuclei. This is Isidore Rabi. Felix Bloch, we again talked about Felix Bloch in the history part, and Edward Purcell, they got Nobel Prize in the year 1952 for their discovery of new methods for NMR precision measurements and discoveries in connection therewith. So, these are Bloch and Purcell. Richard R. Ernst from Switzerland in the year 1991 for the contributions to the development of the methodology of high resolution nuclear magnetic resonance spectroscopy. Kurt Uttrich from Switzerland, I already talked about his contribution for the development of nuclear magnetic resonance spectroscopy for determining the three-dimensional structure of biological macromolecules in solution. As I talked earlier, he is the first one, or in the group of people who have first solved the structure of protein using NMR technique. This is Kurt Uttrich. And Paul Lauterbach from US and Peter Mansfield from United Kingdom at the year 2002 for their discoveries concerning magnetic resonance imaging or MRI. So, these are the two people. So, this is the list of Varian Prize winners. In 2002, Jean Jenner for two-dimensional NMR. In 2004, Erwin L. Hun, professor from University California Berkeley for spin echoes. In 2005, Nicholas Bloombergen, University of Arizona for nuclear magnetic relaxation. In 2006, John Wugg from MIT for average Hamiltonian theory or AHT. 2007, Alfred Redfield from Brandeis University for spin dynamics. 2008, Alexander Pines from UC Berkeley and Lawrence Berkeley National Laboratory for cross polarization. Albert Overhauser from Purdue University for NOE and dynamic polarization. Martin Karplus from Harvard University for Karplus equation. Gareth Alan Morris, the University of Manchester for inept. Ray Freeman in 2012 and Weston Anderson for nuclear magnetic double resonance. So, for times constant there is a huge list. I am not going to the Lucian Prize winners, I am keeping it for you guys to take a look. So, I am finishing this with a collection of cartoons from different NMR aspects which you could go through and enjoy. With that, I am finishing this class. Thank you very much for listening.